Now we are doing the experiment of Hall effect, and the aim of the experiment will be to determine the carrier concentration and Hall coefficient in a given semiconductor using Hall effect setup. And then we have the apparatus used. The apparatus used is going to be the Hall probe. The Hall probe is this device. It's also called as a 4 probe. And then we have the Hall effect kit, which is that machine over there. And then we have the electromagnet, which are these two cylindrical spirals here. And we have the formula n is equal to 3 pi I divided by 8 into 1 by slope per m minus 3. And then we also have the R, which is equal to 1 by any meter cube per coulomb. We have I, which stands for current through the sample, which is Ga. We have RH, which is Hall coefficient. We have E, which is charge of the electron. We have T, which is thickness of the sample in centimeter. And then we have the formula for the slope, which is delta V by delta B into V by T, where delta V is change in the Hall voltage, which is in millivolts. And then we have delta B, which is change in magnetic field, which is in D. And then on the left side, we can see the diagram of the Hall effect experimental setup, which is in the figure 1, and then which is figure number Roman number 1. And then the figure Roman number 2, we have a graph which is used by plotting the graph of Hall voltage versus magnetic field, with Hall voltage being in millivolts on the y-axis and magnetic field being in Teslas in the x-axis. And now we separate these both parts from the apparatus and we keep it here. And now we have this cube of 1 centimeter. And then we keep this block in between the two electromagnets and we make sure that there's a distance of 1 centimeter between them. And then once you're done in separating the both electromagnets with a distance of 1 centimeter, you take the cube off or the block off. Then we turn the apparatus on, and then we keep the probe current into 0 by turning the fine in such a way that it sets itself onto 0. Now you can see that it's on 0. And now you can see that the Hall voltage millivolts is 0, and then we also turn the fine of the probe current, which is a milliampere, to also 0. We turn both the fines on the right side into making the Hall voltage in millivolts into 0 and the probe current in milliampere also into 0. And we also set the magnetic current, which is also milliamps, to 0 by turning the fine. Now we see the procedure again. You can see that the probe 0 is set into 0, and then we should use the probe current to set it into 70 milliamps, which we're going to do now. And then you can see now that we're turning the fine in such a way that it becomes 70. So we're turning it into 70 milliampere. And now as you can see that the meter has become into 70 milliamps. Then we keep the semiconductor material between the poles in a direction perpendicular to the magnetic field, which we are doing right now. Then we are going to vary the magnetic current in increasing order of 50 milliamps and note down the corresponding Hall voltage. So that we have set it into perpendicular, we go to the next step. We set the magnetic current into 50, which we can see now. Then we turn the first fine knob so that it becomes 50. And now it has become 50. And in the first column, as we set the magnetic current, which is a milliamps, into 50, we're going to have to increase from 50 to 100 and so on. And then the next column, the second column, we're going to note the average current, which is field into 10 to the power minus 4 Tesla, which is for 50 milliamps of magnetic current will be 346. So we write down 346 right in parallel of 50. Then now we are going to do trial 1, which is 0.83. And then based on the apparatus, values will be different. And after we set it 50 milliamps, now we are going to set it to 100 milliamps. Now that once we have done it on 100, you can see that you're going to get 165 over there. Because you got 1.65 over there, we can change it can change from apparatus to apparatus. And in the previous apparatus, in which was the manual is written, we have got 1.65 for 100 milliamps of magnetic current. But in our case, we got 165 instead of the 173 or 1.73. So we are going to note down 1.65. It is in your case. And then now we are going to jump to the final value itself, which is going to be 500, because anyways you can do all the values from 100 to 150 to 200 yourself. They're just going to show you the final value so that you get an idea of how to do the experiment. And then now you can see that we have gotten a value of 500 in the magnetic current, and you can see for the 500 the Hall voltage produced will be 8.30, 8.29. It'll be fluctuating, but just get the first value that you see. In the previously done apparatus we got 8.16, but in this apparatus we got 8.30. So in your apparatus, whatever value you get, you're going to note that down. For trial 2, you're supposed to pull the apparatus back, you're supposed to turn the apparatus off, and then you're going to wait for 1 minute until we put it back together like the way it was before. And then once you turn it off, everything should be set back to 0. And then once you turn it back on after 1 minute, you're again going to set all the fines to 0, and then you're going to repeat the experiment again for the trial number 2. You can see after 1 minute and after turning it on, we again set all the dials again to 0, and then like previously done, we're going to set the probe current, which is in milliamps, back to 70, because it's trial 2, so we're going to repeat whatever we did in trial 1 again. And we do trial 2 again. As you can see, we're again setting the magnetic current to 50 milliamps like we used to do before. And then we're gonna write down the values again, and then we're gonna take an average in the end of it. We're going to add the trial 1, trial 2, and then we're gonna take an average of both of them. And then using that, we are going to plot the graph, which is Hall voltage on the y-axis, and we have magnetic field on the x-axis. And then after plotting the graph, you should make the slope, and then you should apply this formula, and this is all the given values, which is the thickness of the sample is given, then we have all the, and then we have the current through the sample, which is given, charge of the electron, which is given, and the slope of the graph, which you're going to find out. Then we apply the carrier concentration formula, which is 3 pi by 8 into b by v into I by et, which is equal to 3 pi I 8 by et into 1 by slope, which you get the answer of 9.1992185 into 10 to the power 22 per millicube. And then from the carrier concentration n, which you got in the previous formula, you're going to put it here in this formula, which you're going to get 1 by Ne, and E is the charge of the electron, which is 1.602 into 10 to the minus 19 meter per coulomb, millicoulomb, and then you're going to just put the value, and then you get 6.794055 into 10 to the minus 5 millicube per coulomb. And then using this, we have gotten the Hall coefficient RH.